Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome to Lecture 3 on Characterization. Today we are going to look at some of the more sophisticated ways to measure temperature at the small scale. These are thermoreflectance techniques, micro-Raman, and these are the ones that are used to measure thin film thermoelectric property that we will see in later lectures. I also describe a technique that is used a lot to characterize nanowires and other low-dimensional structures which are suspended heaters. So let's start with thermoreflectance. Thermoreflectance is a case that you have a surface or a device, you want to measure the temperature, you shine light, and in the amount of light reflection, from that you can measure temperature. The idea is reflection coefficient is a function of temperature. So the device needs to be modulated. Why? Because the change in reflection with temperature is a small effect, is 1 part in 10,000 to 1 part in 100,000. So by just a DC measurement, you cannot detect a small change in reflectivity. But if the change is periodic, you can lock in. So this is the effect of temperature variation is also periodic, and that is translated in the periodic change in reflectivity. And with a technique such as locking technique, we can detect that. Here is a review article that summarizes quite well some of the recent advances in CCD-based thermoreflectance. And the basic idea is that the change in reflection is directly proportional to the temperature by a thermoreflectance coefficient, which is a material property that comes because the material index of refraction, band gap, and other optical properties are changing with temperature. But again, it's a small effect. 10⁻² to 10⁻⁵ for most materials. Here is some of the early measurements of temperature. This is our test device, a micro refrigerator. In this case is 50 by 50 micron. Here you can see the reflection of a laser spot, almost like a pointer, that is going from this location. And then the device turns on and off with a frequency of 1 kilohertz. By some calibration, we are able to measure temperature versus current applied. You can see very nice cooling curve. These type of single point measurement were pioneered by groups of Claes, Fournier, Delaire, Tessier, and all, mostly in France. This is very precise. The main difficulty is it just gives you temperature at 1 point. If you want to scan and obtain the temperature of the device, you have to make sure you have a very stable scanning mechanism, but it will take overnight to get a full image. The first advance was to do parallel locking amplification. In this paper review of scientific instruments, James Christopherson et al. Showed that you can actually make a 256 channel locking amplifier and obtain images of devices, and from that obtain thermal images quickly. So basically you have here 4 devices. The one in the center is biased. At a given frequency, let's say 1 kilohertz, you measure the change in reflection. The surface of this device, the reflection coefficient of this device is slightly different from this, but by doing the locking, you can exactly detect that, and you can even see the heating nearby in the silicon surrounding region. This was has a very high sensitivity down to 6 millikelvin. 256 channel give you images that are 16 by 16 pixel. It's very pixelated, so you can scan it to get higher number of pixels. For example, with this image, it was done some scanning, so it took about 10 minutes. It's still much better than doing the measurements overnight. But now, today, we know that we can do even better. The state-of-the-art CCD-based thermoreflectance have resolutions of 0.1 degree or lower, sub-micron because we are using visible light. Diffraction limits is 2 to 300 nanometer, and time resolution that have been pushed down to 100 nanosecond and then 800 picosecond with a full megapixel image. This is the kind of system that commercially could be purchased. I will discuss now a little bit how you measure the time resolution, because this is something is needed for some of the thermoelectric measurements. We need to do transient, for example, Raman technique, so fast measurements of temperature are important. But from an optical point of view, this looks like a regular optical microscope. It's just the camera and electronics associated with it allow us to do very fast locking detection, either in frequency and time domain. Here is a recent paper that just came out a couple of months ago that describes how this time domain thermal imaging is done. Basic idea is if you want to get 100 nanosecond resolution in time, you take a CCD camera that is typically slow. Frame rates or video rates, 30 frames per second. Per second. Within each frame, you can apply multiple pulses to the device. If the device is fast, the device heats and cools with time that is much, basically it equilibrates before the next pulse arrives. But during this whole frame, you can send pulses of LED at a given delay to the beginning of the electrical pulse. You are basically monitoring reflection coefficient at that time, and you average it. Then in the next frame, you can average before the electrical pulse arriving, and by differencing, you can see what is the change in temperature, and the time resolution, instead of given by the frame rate of the camera, is given by how short is the optical pulse. This technique can be applied to fast devices, but how do you make a fast cooler? Here is the same cooler I showed before. You basically have a superlattice of silicon, germanium, electrical current coming from the side, and current going down, evaporative cooling happening here. Then you have some Joule heating in the substrate, some Peltier effect in the superlattice substrate junction. Typical electrical devices like this can work to megahertz, but it's very hard to get very short pulses, because electrically you can have interference effects. When you send an electrical pulse, there could be reflections from different locations. How do you solve this impedance matching? This is the same device top view, where you can see a ground signal ground. Basically, the electrical pulse go through this configuration, and the geometry and the dimensions are chosen so that this is 50 ohm. So when you have a very short electrical pulse, it's not distorted as it goes from the electrodes to the device, and then the current arrives here and circulates back, and you get the very fast thermoelectric effect. These are the very fast, some of the fastest Peltier coolers. Here are the images obtained under forward bias and reverse bias at different time scale. Again, we apply a given current of a couple of 100 milliamp. You see it takes about a couple of 100 to 150 nanoseconds to see some cooling on the forward bias and heating on the reverse bias. You see this spot heating, which is actually coming from a defect in the device. Basically, electrical current flows from the side contact to top of the device, and because the metal coverage at the edge of the device is low, it creates heating, and you can see how the heating is localized at those locations. Once you have the forward bias and reverse bias, you can process it and get the Peltier and Joule component. Basically, Peltier component changes sign with changing direction of current, and Joule component doesn't change sign. That's a good way to separate the different physics. You can see the Peltier effect is really concentrated at the metal superlattice junction, while the Joule effect happening everywhere, including at this, for example, bad electrical contact. These bad electrical contact don't show up in the Peltier image. So these are examples of how fast thermal imaging can be used to distinguish the physics of where is the Peltier and where is the Joule effect. How you can push it even further. Here are some of the thermal images with record resolution of 800 picosecond on a full image. Again, these are kind of megapixel type CCDs. You have two copper metallization that are separated by the tiny via. Basically, there is a 500 nanometer via between the two. You cannot see it by eye, but when you send current, you see the heat, and you see how the heat at 17 nanosecond up to 96 nanosecond is going around a via that is submicron. These are ways that we can kind of push the limit and look at ultra-fast thermal effects. Here is the measured heating on two different vias, 350 nanometer via and 550 nanometer via, with times up to 150 nanosecond, but the first time steps go to 800 picosecond, and you can see, you can observe 7 to 15 degree heating at a very small locations quite precisely. These are the results which were presented a couple of years ago at the International Heat Transfer Conference. How do you get from a measured reflection to a value of the temperature? You need to know the thermoreflectance coefficient. This is something that you can look at it in the handbooks. Thermoreflectance coefficient in the units of 10⁻⁴ per degree Kelvin or per degree Celsius is given for gold, titanium, nickel, and aluminum. You can see that most of these curves have a shape that has a peak at some point, and it could be positive or negative. That has to do with the resonant electronic interactions and how they shift with temperature. Basically, by seeing how the thermoreflectance crosses zero, we know what are the resonant electronic interactions. Typically, we use an illumination color that maximizes the thermoreflectance coefficient. That's the highest sensitivity we have to measure temperature. So for aluminum, we need mostly IR colors, but for gold, we can go to visible wavelength. Titanium and nickel have a smaller dependencies. But often, nanoscale material and devices are not made from pure materials. How one calibrate for such thermoreflectance? The idea in principle is easy. I have, for example, a surface. On top of it are the devices and integrated circuit. I measure the amount of light reflection with a usual microscope, and I put this on a temperature-cooled thermoelectric stage. This heater applies a periodic temperature variation that is measured by a thermocouple. So this gives me the variation in temperature measured by an external sensor, and if I have at the same time the change in reflection coefficient, the ratio of the two can give me the thermoreflectance coefficient. What is the real challenge is the thermal mass of this thermocouple should be small enough so that it measures the temperature of the surface accurately. For this, you need typically 1-2 mil thermocouple on the surfaces. If it's too big, the time response of this could affect it. The other point is that the contact between here and the surface needs to be as good as possible thermally, because you don't want to have temperature differences. And these are the usual challenges in measuring temperature at a small scale that you will see in the following lectures when we discuss measurement of the Seebeck. So assume that you have two surfaces, you measure light reflection, and you put it on a temperature control stage, you get thermoreflectance coefficient of surface 1 and surface 2. A challenge arrives when the surfaces are covered by a dielectric layer that is semi-transparent. Basically, the light can do back and forth some Fabry-Perot resonances in the transparent layer, and this changes the reflection coefficient. Whatever changes the reflection coefficient can also change the change in reflection with temperature, the thermoreflectance coefficient. And because this is two effects, one, the temperature change, how it affects the reflection at the surface, and how it changes the dielectric constant here is very hard to separate. Here are some of the measurement done on a piece of silicon with oxide or nitride. Here is the measured reflection versus wavelength. No change in temperature yet, and you can see that it's lots of oscillations. This constructive and destructive interferences come because of this dielectric layer. This is one way people actually measure thickness of dielectrics, by the color, how it looks like. And whenever you do temperature changes, you have to worry about where you are exactly at this wavelength. One possibility is to use a broader illumination source, so you kind of average over this to avoid this interference effect, and that has been used successfully. Now let me shift gears and describe another optical method to measure temperature. This is called Raman, and for measuring on the small scale it's called micro-Raman. The basic idea is that if you shine light to a material at the central wavelength, in the light that is coming out of the material, the color could be slightly shifted, and it could be either at lower energies or higher energies. And this energy difference is coming because of various vibrational energy states. The key idea of the Raman is that the position of these energy states or the position of these Raman peaks is temperature dependent. That could be used as a thermometer. Another effect is that the ratio of the Raman peak at lower energy to Raman peak at higher energy is given by the population of these two energy levels. And the population is given by Boltzmann factor. It gives us an indirect way of measuring temperature directly. So by looking at the ratio of the two, you can measure the temperature, and that is described in this reference. That's a common technique. Here is an example with our, again, toy micro devices, how it's done. In this case, here you have a micro heater, and we are scanning from near the device to away. Here is a simulated temperature profile of the microheater, and we are scanning from the surface from next to the device a little farther away. Here is the measured temperature difference from 8 degrees Kelvin next to the device down to 0, just 6 micron away. And you can see the data points that you can measure temperature with micron resolution. The temperature resolution is typically on the order of 1 degree. It's noisy because this is a scattering effect that is weak, so you need to average it for a certain time, and there's other effects that could happen. But one unique characteristic of the Raman is, because you can do confocal microscopy, you can use a wavelength of light that penetrates in the material. One is able to measure temperature versus depth, and that's something that most other surface technique cannot do. So the basic idea is that you do confocal, you measure the reflection from the Raman signal from a certain depth, let's say 2 micron in the device. And again, by looking at the ratio of the stocks to anti-stocks, this is the two Raman peaks, you can get the temperature. It's very noisy, but it can give you a three-dimensional temperature profile that is very hard to obtain with other techniques. Of course, this is limited by the penetration of light, and you have some effects because of a light pattern inside the material could include some regions that are hot and could affect some of these Raman measurements. Let me finalize. The last topic for today is how do you, now that we have seen how you measure temperature, how do you characterize heat fluxes and get thermoconductivity of nano objects? A technique that has been pioneered by Arun Majumdar's group, and Li Shi and others have contributed quite a bit, is you fabricate a tiny heater platform on a silicon chip, and you isolate it with long beams in a way that this is a localized heat source, and you can measure the amount of heat flux. Then you place a tiny object like a nanowire, carbon nanotube, or other type of device between the two. This placing is extremely challenging. It requires patient students who can do a lot of trial and error. Sometimes they use pick and place with AFMs. But once you put it there, it's important to ensure there is good thermal contacts. And in papers by Li Shi, they discuss quite a bit about this. But then once this is done, the measurement is quite straightforward. You just send some current to a heater. That current creates heating. With a couple of microamp, you can heat, let's say, 1.5 degrees on this heater. Because these two are isolated from each other, the only reason this one heats up is because of the heat transfer through the nanowire. So this is the heat transfer happening through the nanowire, and on the other side is a tiny temperature increase, less than 0.1 degrees, but you can still accurately measure it because a resistor is a nice thermometer once you calibrate it. From the ratio of the two and the heat fluxes, you can actually calculate thermal conductance. This is a technique. In the last 10-12 years, people have measured figures such as this. This is from Li Shi's group, thermoconductivity of various carbon nanotubes, a single wall carbon nanotube, 148 nanometer bundle, 10 nanometer bundle, the multi-wall carbon nanotube bundle, 14 nanometer, and 1 to 3 nanometer CVD grown single wall carbon nanotube with the highest thermal conductivity. So these are the kind of examples you can do with this suspended platform. There are lots of research recently. If you have a nanowire, what is the impact of the surface roughness? Here are some measurement of silicon nanowires that was summarized by David Cahill. This is old Arun Majumdar's data, but basically in some smooth nanowires at room temperature, you measure thermoconductivities that you can explain with existing theories with our understanding of the surface. But when the surfaces are rough, this becomes substantially lower, and that was a place that is a lot of excitement because you can get ZT values maybe close to 1 at room temperature. This is an active area of research. I should now, just the last view graph, this type of suspended platform were also used by Keith Schwab and Ruckus group to measure what is the quantum of thermoconductance. And this is something that you don't hear it as much in the lectures by Professor Datta and Lundström. You heard about quantum of electrical conductance. But by making by a suspended platform that are connected but very small thermal bridges, they are able at very low temperatures below 1 Kelvin to observe that the heat that is flowing through this is quantized, and this is given by the quantum of the thermal conductance. So this is kind of one of the key advances that allowed us to measure such precise temperatures. Let me summarize. In this lecture, you saw specifically thermoreflectance imaging, how you can do steady state and transient measurements. The spatial resolution is down to 200 to 300 nanometer, temperature resolution easily less than a degree or 0.1 degree, and importantly, time resolution could be less than a nanosecond, up to down to 800 picoseconds. We discussed that to get really beyond an image, a calibrated temperature, you need to calibrate the thermoreflectance coefficient of the surface. There are some challenges that one has to be aware, but one could obtain quantitative results. I also discussed about micro-Raman as another technique, which is optical. It's not as precise, it's not imaging, it's point by point, but the advantage of micro-Raman is that it can give you the three-dimensional temperature profile. And finally, I discussed that you can use suspended micro platform, NEMS type of platform, to do measurement of heat transfer at the smallest scale. What we will do in the next lecture is we will use the technique used so far, and as well as the previous lectures on scanning thermal microscopy, to describe how thermoelectric properties of thin film, Seebeck, as well as ZT and others are measured. And look forward to see you at the next lecture.